We're used to seeing the ocean from above, where we have a deep body of water with waves propagating at the surface. But because the ocean is heated from above by the sun, the upper part of the ocean is warmer and less dense than the cold water beneath it. This produces stratification where a warm surface layer overlays a colder deep layer, and these two layers are separated by a pycnocline. If we zoom in on this internal stratification, we discover that like the fluid interface between air and water, this pycnocline can support waves, which we call internal waves. In the Arctic Ocean, however, instead of warm waters overlaying cold waters, the ocean is stratified by salinity due to a combination of large volumes of freshwater input into this region and non-linearities in the equation of state for seawater. Here, instead, cold but fresh waters sit on top of salty waters, an example of which is shown here. Although the Arctic Ocean is quite quiescent, like the rest of the world's oceans we can find internal waves here too. These waves induce flow in the fluid, where in the upper layer, fluid travels in the same direction as the wave, and in the lower layer, fluid travels in the opposite direction. When waves at the surface interact with structures such as a beach or a jetty, it produces chaotic, turbulent processes. Likewise, when these internal waves interact with structures in the ocean, mixing will occur between the upper and lower layers, which in the Arctic Ocean could bring heat from the deep waters to the surface, where it could then melt ice. So, when we have ice at the surface, we want to understand both how these structures move with the flow induced by the internal wave, and in turn, how these moving structures will interact with the flow and induce mixing. To answer this question, we bring the system down to the laboratory scale. In a 7-metre long wave flume, we set up a stratification with dense salty water at the bottom and fresher water at the surface. A removable barrier at one end of the tank allows us to set up a lock gate experiment, where a further volume of the fresher brine is added behind the gate, causing the pycnocline to be discontinuous across this region. We add in our model sea ice, polystyrene floats which are weighted with lead so that they match the density of sea ice. When we remove the gate, an internal wave is produced and propagates down the tank from right to left, and we investigate how the ice and the flow interact with each other. To find out more about these experiments, come to my E2U talk in the Nonlinear Processes 7.1 session, drop me an email, or keep up to date by following me on Twitter.